Hello, everyone, and welcome to the Mastermind Masterclass. My name is Candace Chapman, VP of Marketing here at Genomenon. Today's Masterclass focuses on maximizing results by properly using sensitivity and specificity in genomic search. Mastermind was created to make it easy to find relevant genomic insight from the medical evidence. And in the tug of war between sensitivity and specificity, our approach has been to first maximize sensitivity and then optimize specificity within the scope of maximal sensitivity for the most efficient workflows and the best results. Today, our co-founders, Steve Schwartz and Mark Kiel, will cover some recent advancements in this area for Mastermind and go in depth on how to make the best use of Mastermind Genomic Search Engine. If you've registered for this webinar a while ago, you may be asking, where is Myriad? Good question. Dr. Catherine Dye from Myriad was scheduled to join us for this webinar to discuss how they use Mastermind as it relates to sensitivity and specificity. But I'm sorry to say she's now unable to be here, but we are working on rescheduling a different day for her to speak. So stay tuned for more information on that. Some of the features you'll see in today's masterclass are only available in the professional version. So if you currently have the basic edition, this is a great time to get reacquainted with the full functionality of Mastermind and see if you and your organization can benefit from Mastermind Professional Edition. It's always our goal to make Mastermind the first resource you use when interpreting variants, and I hope that this deep dive masterclass will help you get the most out of it. Let me just quickly cover some housekeeping items before we get started. You can submit questions in the question box at any time during the presentation, and we'll have a Q&A session with Mark and Steve after the demo. Today's masterclass is being recorded, and a link to the recording of the presentation and the Q&A transcript will be emailed to you in the next few days. And that's it, nice and short. So let's get on to our speakers. Once again, we've gathered our two amazing founders to discuss Mastermind in depth. For our master classes, I like to keep things casual. So for our speaker introductions, this time I asked our founders to answer the question, what is the most beautiful place on earth? And our first presenter, Dr. Mark Kiel, co-founder and chief science officer, he remembers finding a small overgrown pond in a wooded area between two farms behind his neighborhood when he was exploring at 10 years old. And he thought he had discovered it and no one else knew it existed. So that sounds beautiful, Mark. Our second presenter is Steve Schwartz, co-founder and chief technology officer. And Steve says the most beautiful place in the world is almost anywhere that comes up in a screensaver. And that one day he'd like to do a screensaver journey of the world. That sounds amazing. And you've got to do that and get out more, Steve. If you want to know more about Mark and Steve, check out their blog posts on genomenon.com. But for now, let's welcome Mark to start the presentation. Hey, Mark.
Hey, thanks, Candace. And thank you all for attending and welcome. Kathy does send her regards. By now, Steve and she and I and all the crew at Myriad are pretty good friends, having worked closely together, bringing up Mastermind in their workflow, and she's looking forward to communicating with all of you when we next get the masterclass where she'll attend scheduled. But for my part, I'm going to begin with an introduction of what Mastermind is for those of you who are less familiar, and I'm going to speak specifically to how the sensitivity of Mastermind's results and the specificity capabilities of Mastermind's feature set optimize your variant interpretation and literature curation workflows. So I'll begin at a high level and say that Mastermind, the user interface, is a decision support tool meant to be used in clinical workflows in its professional version. And what the data of Mastermind comprises is an index of the empirical evidence in the published literature. And what we're extracting out of that information, the many tens of millions of titles and abstracts that we index on a nightly basis, and the still many millions of full text articles and supplemental data sets that we index include in Mastermind on a weekly basis, is pulling out diseases, genes, variants, and all associated biological concepts that inform the variant interpretation workflows that our customers use Mastermind for. So Candace, if you could take it to the next slide. The next slide here describes what our value proposition is. So it's often considered that Mastermind just organizes the evidence, which should be apparent to any users of the software. But we do an additional thing that I alluded to just a moment ago, and that's identify those associations. So not only do we understand where all of these terms appear in the content that we index, but we also bring them together for you based on the nature of your searches. So organizing that evidence, annotating it, and then identifying those associations de novo, very comprehensively across all of the empirical evidence, is what Mastermind specializes in and the value that we bring to our users. So this is a nice schematic that Steve, who you'll hear from in a moment, devised to characterize what those associations are and to allow people to visualize how that can be valuable in their workflows. So let's start on the left there with the hexagon, with those nodes on the periphery being a reflection of any of those genomic concepts that would inform your workflow as you're interpreting variants. So naturally, you begin with a need to understand where genes and gene synonyms are mentioned in this content. And then more deeply, any time that there's a gene anywhere in any one of these references that we index, we comprehensively index the rest of that paper for the mention of any genetic variant, no matter how it's described, in any one of those genes. So genes and variants form sort of the core of the genomic associations that we're identifying and indexing, around which you can decorate that information with the mention of any associated disease and or phenotype or phenotypes, any therapies that have either been tried or that are validated to be efficacious in the context of those diseases that are resulting from any one of those genetic variants. And then lastly, at the bottom would be categorical key terms that are appropriate to variant interpretation that we can sort of crudely fractionate into clinically related key terms, as well as functional, either intrinsic to the variant or based on empirical studies, either in vivo, in vitro, or even in silico. And it's important to note then, as Steve has schematized there, that you can enter this hexagon or our data at any one of those nodes or multiple of those nodes and have results returned to you at any one of those nodes as well. And then on the right side, what we're illustrating there is the more associations that you have from this empirical evidence, the stronger the relationships are, the higher value that information, and Mastermind can bring all of that information together for you and provide you with quantitative insight into what associations are most relevant to what you're doing in the clinic. So the next slide allows me to speak to, although we won't go into much more detail, one of the ways that Genomenon provides value for our users beyond the obvious, which would be the basic search engine, which we provide for research use, the professional version of Mastermind, which is used by all of our clinical users, and or the API, which our clinical users in high volume labs take advantage of for deeper integration of the Mastermind content into their workflow. This is a less well-known way that we deliver value among our clinical users, but we have a number of pharma attendees on the webinar, so I wanted to be sure that I described how Genomenon can produce comprehensive genomic landscapes, which is to say a database of all genes and their variants, curated to clinical standards for any disease indication or drug development program. And that data is curated very efficiently and very accurately according to those clinically accepted standards and provides our clients with key insight into the pathogenic mechanisms based on those clinical studies, empirical functional studies, treatment and trial information, and all of those scientific assertions come supported with reference citations from the medical literature, all summarized for efficient use of that data, and then updated on a quarterly basis so you're never behind any of the cutting edge research that informs your gene pathway, your indication, or your therapeutic target. So the last thing that I want to say before passing it over to Steve, who's going to go into a little bit more depth about sensitivity specificity, before he turns it back over to me for a demo of several use examples in the Mastermind software, is just writ broadly, Candace alluded to the tension between sensitivity and specificity. I like to think that Genomenon through Mastermind has harmonized the otherwise competing aspects of maximal sensitivity and enhanced specificity, where she's quite right that we first prioritize maximal sensitivity and then allow the features of Mastermind to have the users tune for specificity of results. So a couple of high-level things to keep in mind that pre-existing in Mastermind's database are the sensitivity of our content coverage. We've alluded to that already in the form of the many millions of prioritized genomic articles that we've indexed at the full text level, including figures and tables and very complicated descriptions of these genetic variants, as well as the supplemental data for which we have the most comprehensive data set available in the world. But then also the sophisticated algorithms that we use to automatically index this content, which we've referred to as genomic language processing. The most simple instantiation of GLP would be all of the gene synonyms and aliases and nicknames. That's one of the facets of GLP. The more complicated facet of GLP would be all of the idiosyncrasies and nuances of genomic variation nomenclature. Variants can be described as RSIDs or as protein level changes or cDNA level changes. They can be faithful to the standardized HGVS nomenclature or much more typically deviate, sometimes substantially, from that nomenclature. Mastermind's genomic language processing takes account of all of those nuances and disambiguates and organizes the data appropriately. We cover coding and non-coding variants alike, as I'll showcase in some of my examples, all of the transcripts of any one of these genes, as well as the legacy nomenclature, which I'll speak to another one of the examples that I'll highlight. So that's the sensitivity part. The specificity part, as I suggested, would be in Mastermind's allowing the user to modify their search criteria. And again, I'll speak to this in some examples, but it comes in a couple of flavors: the disease, phenotype, and therapeutic ontologies that we allow users to add, sometimes in multi-parameter combinations, as well as those categorized key terms, and the ability that users have to perform free text search to get the maximally prioritized content based on the nature of their clinical question and circumstance. And then the last thing to say before I turn it over to Steve is Mastermind, as I'll show, visualizes the reasons behind that prioritization and allows users to rapidly confirm the accuracy of those prioritizations and get the information that they need to drive their clinical interpretation. So with that, you'll see me again momentarily, but I'll let Steve talk to what he and his dev team have recently brought to bear in Mastermind to even further enhance the sensitivity and specificity of our user search results, again, based on user feedback and in close collaboration with many of our high volume and engaged users, Myriad included. So Steve, let me pass it over to you, and I'll sit tight until you pass it back to me for the demo examples.
Okay. Here we go.
There you go.
Can you see my screen yet?
Yep, we see variant nomenclature, Steve.
Oh, great. Perfect. Okay. Here we go. Okay, so thank you very much. As both Mark and Candace described, when we talk about evaluating the value and utility of a given set of data, we often characterize the value and utility by sensitivity versus specificity. So by sensitivity, what we mean is the proportion of true positive results that are returned in the result set for a given query or search. And by specificity, we're talking about the proportion of negative results, meaning results that should not match your search, that are excluded in the results. And when we talk about the two of those being sort of a compromise or at odds with each other, in general, when you increase the sensitivity of your data, of your algorithms, of your search criteria, what you're really doing is you're introducing more results into the result set, which introduces more positive results, but also tends to introduce more false positive results, meaning results that come back in your result set that should not be there, that are not relevant to what you're trying to find. And then as the corollary to that, as you increase specificity, what you're really doing is you're removing results from your result set, which removes results that shouldn't be there, but it can also tend to remove results that should be there, which introduces what we call false negatives into the result set. So when we talk about the sensitivity and specificity of our data, one of the things that's unique to Mastermind is that we have to worry about this on multiple fronts. We have to worry about sensitivity and specificity, well, sensitivity as Mark described, in the source data that we're analyzing, being the evidence and the medical literature and the supplemental data. And we also have to worry about it in terms of how an author describes a given genomic entity, in this case, a variant. We have to worry about the nomenclature that the author uses, whether they misuse the nomenclature or not, how much information they include in their description of the variant. And then the third aspect is we have to worry about the sensitivity or specificity of the user search, meaning how does the user search for a given variant in Mastermind? And then we have to marry those, we have to marry the data with what the user is searching, meaning we're sort of dealing with a compromise of sensitivity and specificity in multiple dimensions at the same time. So one of the things that we talk about often internally when we're discussing sensitivity versus specificity in the context of variant nomenclatures is we often will characterize different variant nomenclatures into two categories, where the first category is a nucleotide-specific nomenclature and the other category is codon-specific nomenclature. So a nucleotide-specific nomenclature is a variant nomenclature that describes exactly which nucleotide changed for this variant. This G changed to this C, or vice versa, or whatever the nucleotide change was. So a nucleotide-specific nomenclature includes genomic coordinates, cDNA nomenclatures, RSID, and even the older, more obsolete IVS nomenclature. Whereas a codon-specific nomenclature doesn't describe necessarily which nucleotide changed and what the nucleotide change was. It describes more directly the biological effect, meaning it describes what amino acid change resulted from the underlying nucleotide change. When we talk about sensitivity versus specificity, as Mark mentioned, we tend to optimize for maximal sensitivity and then optimize the specificity within the context of maximal sensitivity. And the reason we do this, another way of putting that is if we have to err on the side of sensitivity or specificity, we choose to err on the side of sensitivity. The reason for that is because it tends to be the much less egregious error to make, in that if you err on the side of maximal sensitivity, you might have more false positive results. And false positive results you can come back from because you can analyze and validate the results that you have and decide which ones are not relevant to you. Versus erring on the side of specificity makes you less able to recover from that because you can't analyze and validate or invalidate the results that you never got. So when we look at the nomenclatures here, again, sort of the most specific nomenclature you can have is the genomic change, the genomic coordinate. From there, you still have nucleotide-specific nomenclature of cDNA. However, that is transcript specific. And as you can see here, you can have overlapping transcripts where the same genomic change results in two different cDNA descriptions. What's even more confusing is oftentimes an author may describe a cDNA change without specifying a transcript, which means a given coordinate can exist in multiple transcripts. For example, this 5117 coordinate in transcript B also exists in transcript A. It's just not at the same genomic location. It would be over here on transcript A, meaning it maps to a completely different genomic change. What's more is you tend to have about a 1 in 4 chance of the reference nucleotide matching at that position, which means this can be a valid description in transcript A that describes a completely different variant. And the same happens with protein nomenclatures, though you tend to have less of a chance that the reference codon is valid in both transcripts because there's a higher variation. There's more amino acids that can exist at any one location. So these are the kinds of ambiguities that we have to deal with when we're indexing the literature and when we're trying to figure out which results map to your search. So with all of this in mind, we tend to always prefer, or in the past, we've always preferred the codon-specific nomenclature, the protein description of a variant. And the reason for that is because it more directly maps to the biological effect, which tends to be the more relevant concept when you're trying to look at what is the cause of this ailment or these conditions in a patient, for example. So an example of when this affects the user is if you have a patient with C.1799T to A variant, for example, that results in an amino acid change from valine to glutamic acid. However, there might be a paper, and this is a bit more of a contrived example to be sure, because one of these is much more likely to occur than the other, but there are other examples where you might have multiple cDNA changes that are similarly likely to happen. But in this case, you might have a paper that describes C.1799 to 1800 Dellins AA, meaning the TG changed to an AA, which results in the same amino acid substitution. And if you search the literature or the evidence only for 1799T to A, you might miss that paper, which could have a similar or the same effect, and the paper could give you critical evidence for being able to diagnose or treat a patient, or for being able to evaluate the data by and large when you're looking, for example, at the domains or the characterization of variants across a gene. So again, this is a bit more of a contrived example, but there is at least, there's actually several. This is one of several examples from an actual customer of ours where this sort of grouping of variants by the relevancy of the biological effect helped. Now, granted, when I say that we prefer the protein description of a variant, one of the issues with the protein description is there is no protein description for variants that occur in non-coding regions. So, of course, our solution to that was to make one up so that we could have a common variant description across all variants that could occur in the exome. So what we did for non-coding variants, for example, for intronic variants, is we created a protein description called int, where in this case, we would use D936 int to describe all of the intronic variants that occur within the intron that borders or is within the D936 amino acid position in that gene. So again, one example of when this helped with a customer of ours is they actually had a case that they use in a lot of their marketing materials, which said that they had a patient with this variant at the top, C.2888 minus 15 to C.2888 minus 4 del. So it's a 12 base deletion within the intron of this gene. And in their marketing materials, they said this variant has never been published in the literature. We had no evidence to go on, but through our internal processes, our data and our algorithms and our people, we finally determined that this patient had non-small cell lung cancer caused primarily by this variant in this gene. The only issue there, of course, is when I saw this, the first thing I thought is, well, let me search it in Mastermind and see if it comes up with anything. So I typed in their variant as it is here, and Mastermind immediately returned all results, not just for this specific nucleotide change, but everything within that intron. And if I remember correctly, it brought up 4 or 5 articles. One of those articles cited this variant at the bottom, C.2888-16 to C.2888-3 del. It's literally a 14 base deletion centered exactly on the deletion that their patient had. So it's almost by and large the exact same thing. What's more is the article that returned this result, the title of the article is something along the lines of non-small cell lung cancer in patients with intronic deletions in this gene. So it was highly relevant to what they were looking for. And thanks to the way that we were prioritizing and grouping on the protein effect, it was returned instantly. It didn't take me more than a few seconds to find the paper that they had never found. But there are limitations to this approach. For example, let's say that you're looking for an intronic substitution, and let's say this isn't to scale. Let's say this is 20 bases into the intron. So what you're really looking for is a deep intronic substitution, maybe even just on the acceptor side of the intron, and grouping everything as int in that intron might return a lot of results. In some cases, like the previous one, it might only return 4 or 5 results, and it's really quick and easy to flip through those and figure out if any are relevant to you. But in other cases, it might return 200 results, which isn't quite as practical to be able to go through quickly and tell which ones are more highly specific to the variant that you're looking, that you're searching for evidence for. So in this case, the results might include a different substitution that's much closer to the splice acceptor site, or it might even include something more unrelated, like a deletion on the opposite half of the intron that probably isn't what you're looking for. So one of the things that we've done to improve this, especially in the non-coding regions, is we've introduced more highly specific, what we call buckets, or ways of grouping non-coding variants by biological effect, which again tends to be less discrete in terms of what the biological effect is compared to variants in the exome, in the coding regions of the gene. So we've taken the intron and we've divided it into 2 halves, the intron donor half and the intron acceptor half, so that you can further refine your search to just 1 half of the intron when looking at those deep intronic variants. And we've also added splice region groupings of variants as well. So we have a splice region donor and a splice region acceptor, which by definition correspond to variants that empirically have been seen to affect splicing, meaning they might occur in the codon bordering the intron, or they can go from 2 to 8 bases into the intron. An example of where this helps, it might be if the codon that borders an intron, let's say, is the G459 location, then you might have a synonymous variant like G459G, which you might ordinarily look over. But in this case, it would additionally be categorized in Mastermind as a splice region donor variant. So it might indicate that you shouldn't look over that synonymous substitution, because even that synonymous substitution can affect splicing in a significant way. So going back to the first slide that I showed here, keeping all of these things in mind, keeping in mind the fact that you have very specific ways of searching and describing variants as genomic coordinates that can map to multiple transcripts. You also have the nucleotide-specific nomenclatures for variants compared to the codon-specific variant nomenclatures. And I've also kind of shown the benefits of using one versus the other and how those might change and become less clear, particularly in the non-coding regions. But everything that I've mentioned also applies to the coding regions as well. And so when you're thinking through, again, sensitivity versus specificity, keep in mind we have a couple different ways that we're marrying those results. For example, an author might describe a variant in the protein space that might be very ambiguous. You know, something here, like here, G1706A might be specific enough to describe in a paper, but there are also papers that describe a variant as G1706FS or frame shift. That can be a very ambiguous description of a variant because it could be an insertion of one nucleotide, a deletion of one nucleotide, an insertion of two nucleotides, a deletion of two nucleotides, and so on, anything that results in a frame shift starting at that position. This is one of the other reasons why we optimize for the proteins, why we normalize to the protein effect, because we have to take into account the ambiguity of descriptions that authors often provide in the papers, and we don't want to exclude that paper from our results. Again, maximizing sensitivity of the data source is another primary requirement that we have of our data. So we don't want to exclude a paper just because the author didn't satisfy some particular bar of specificity in their description of the variant, because they still might have very important evidence or information to provide for that variant. So in this case, we try, when you do a search in Mastermind, we do allow you to search by any nomenclature, whether it's nucleotide specific or protein specific, and then we show you everything that we know to be relevant to your search, regardless of how you searched it, based on the evidence that we have. Also, again, regardless of how the author described it, so that you hopefully don't have to think about these things too much. So for example, to find every variant, you don't have to search for C.5117G to C or P.G1706A or G1727A or C.5180G to C, just to find every possible way that a variant could be described in a paper for your source genomic change up here. So we do all of that behind the scenes, and then again, we normalize everything to the protein space and then try to show you everything that's relevant while prioritizing the most specific results at the top. So in this case, if you did a search for this genomic coordinate, we would show you all of the articles that cite that genomic coordinate, all of the articles that cite RSIDs at that genomic coordinate, all of the articles that describe either one of these cDNA descriptions, if they did not specify which transcript they're using. So they often don't. They often will say C.5117G to C and not tell you what the transcript identifier is. So we'll show you all of the results that could be describing that genomic change. And again, in addition to all of the results that where the author described the variant at the protein space, again, not necessarily specifying the transcript that they're using for that. So we do all of that for you, but then the articles that specify your nucleotide change get prioritized to the top, because that's sort of the last point that I wanted to discuss, is that while we've always had the philosophy of maximizing sensitivity and then optimizing specificity within the context of maximized sensitivity, our understanding of sensitivity and specificity has also evolved over time. So again, this goes back to the non-coding regions of variants. One of the evolutions of that understanding is that if your results are too sensitive, meaning, let's say in a non-coding region, they include results of variants on the opposite side of the intron than what you're looking for, it can lead potentially to practical false negatives, which is the name that I give to results that are in your result set, but you miss them because there were too many results to look through. So if you do a search for an intronic variant and 200 results are returned, there might be a really good specific result 100 results into the list, and you miss that because it takes too long to go through every result with the same sort of rigor that you would if you only had 5 results to look through. And so with that in mind, that is why we've introduced these new, more specific buckets of intronic variants. And it's also why we've started to prioritize the nucleotide specific matches at the top, so that you have a better chance of always seeing the most specific results, and then you can keep looking down into the more sensitive results if you still haven't found what you're looking for, and not risk missing something because, for example, we've decided to compromise on sensitivity, which is something that we don't want to do. With that in mind, I'd like to turn it back over to Mark now to give some demonstrations of how to use these concepts I just described in Mastermind as you're searching.
Thanks, Steve. Can my screen be seen here? Steve, can you see Mastermind on the share?
Yes, I can see your screen. You're good to go.
Thank you, Steve. That was extremely clear. A nice introduction to the search examples that I'm going to go through. I'm going to go through the 3 most common search results. I'm going to spend a little bit of time talking about those because we have some attendees who've only been using basic or who are brand new to Mastermind. And then I'm going to follow up with about a half dozen more specific examples that illuminate some of the things that Steve talked about with specific searches. So the first search example, all of them will be variant level searches for this masterclass. I type in my gene, I type in my variant. Mastermind makes a recommendation based on its ability to understand what gene and what variant you're describing. You select that variant from the dropdown and execute your search. Just to orient everybody to the architecture of the Mastermind detail page here, the top is where you modify your search terms to get more enhanced specificity. The right side is where we display the literature landscape in your result set that match the terms, in this case just a variant that you've searched on. And then the left is the variant landscape where Mastermind presents your search results in the context of all of the results that Mastermind has indexed for any variant in the gene that you've searched for. So for this example, the first thing that you notice is that there's 11 search results where this variant is mentioned in any one of those references. It's great to use these examples recurrently because every other week or so we get a new number there, and it looks like there's a very recent article from late July that was just recently included here. So this has gone up from 8 to 11 over the past several months. What you can see here in visual form in the publication plot there are all of those 11 references depicted along the x-axis by publication date, the y-axis by the impact score or number of citations for that journal, and then each of those icons representing one of those articles has a size associated with it, which is based on the relevance calculation for your search terms based on the content of those articles. And a couple of the parameters that we use are the number of times that your search term appears in those references, where it appears in the reference, how many other variants appear in that reference in case it's less specifically about the variant that you've searched on. And then if you've added additional search terms, how close together those search terms appear to the mentions of that genetic variant, whether it's the same sentence, same paragraph, same section of the reference, etc. And then all of that information is depicted in list form below in that prioritized order. And so just to put a finer point on what I was just describing, this small dot at the upper right, which used to be the most recent reference but has been overtaken by this reference, that is small because the variant is mentioned maybe once in the supplemental data. It's on the right because it's recent, and it's tall because it's in a decent journal, which is PLOS Genetics. In contrast, you see this bubble or reference, which is at the far left. It's a good journal, Human Mutation. It's the earliest reference for that variant, and it's talked about at great detail in that reference, maybe 6 or 12 times by the authors. And so it's highly relevant to your specific variant search. And then again, all that information is depicted below for each of those references, row by row there, where you can see the bibliographic information and a window into the depths to which the authors describe the gene or the variant. And when you click on one of those rows or one of those references, you see the fully highlighted title and abstract with terms of interest demarcated there in bold, as well as on the right, the full text sentence matches providing context for where the authors described terms of interest. And just to put a more fine point on it, you can specifically see where the authors have described the variant that you've searched on and how they described it and what they've said. And then going back up to the article pane, you can rapidly toggle from reference to reference to review all of the different ways that that variant can be described by different authors. So that's the first search result, where there's between 1 and maybe 12 articles in your result set, where I would just perform the search, march through each of those references in prioritized order, reviewing the title and abstract, reviewing the full text sentence fragments, and then either making your decision about the meaningfulness of that variant or otherwise electing to go into 1 or 2 of those references at the full text level to get a broader context of what the authors are describing with relevance to that variant. So that's the first example. The second example is different in that you'll have returned to you more than 12 references. So this is a common example that I use. It's in the Uros gene. It's a missense variant. There's 94 references that Mastermind has found with its exhaustive indexing across all of the medical literature. That's great because you know it's well covered in the empirical evidence. You'll also note in the publication history how homogeneously prioritized those 94 references are. That's an indication that each of those studies, by and large, speaks to that variant at some depth. So just like Steve had talked about the practical false negatives, we don't expect you to go through every one of those 94 references, and instead we empower you with features in Mastermind to enhance the specificity of your search result depending on the nature of your questions. And the nature of your questions tend to be, are there clinical studies that allow me to inform my variant interpretation, and or are there functional studies? And the way that Mastermind allows you to get to that information is through those categorized key terms. I'll just, for the sake of brevity here, I'll go right to the need in this use example to find functional studies. I'll click on the functional subcategory in the ACMG AMP interpretation category. I can choose to enable all of these keywords, enable a subset, just say the in vivo functional studies based on keywords, as well as toggling on and off any of these terms a la carte, where I'll point your attention to the numbers next to each of these key terms, which makes reference to the number of those papers out of the 94 that were in your total result set that mention that key term. Most of our users, most of the time, rely on the expert ability of Mastermind to perform a relevance calculation that fits their needs, and so they cast a wide net and have all of the functional key terms into the prioritization and then submit with those chosen filters. And what happens with a search like this, when you've got more than 12 references and you want to enhance the specificity, is you filter out content from those 94 references that don't talk to any of those key terms that you search for. And secondly, as you can see here in the publication history plot, you'll see a very dramatic reprioritization of the content based on your declaration as a user that you care about those functional key terms. So again, this is now a much more enhanced specificity of the results that Mastermind delivers based on your declaration of an interest in functional studies. So just like I did in the first use example, I'll click on the topmost prioritized reference and see immediately, based on the title and abstract, that it is a knock-in mouse model of this variant that recapitulates that human disease. And Mastermind, just as I described before, allows you to see at a granular level exactly why that reference was prioritized. When I toggle to the keyword sentences only, you can see here which keyword or keywords were mentioned in the study and in what context the author described them. And then again, to toggle from reference to reference, if that paper was insufficient for your question, you're looking for a different functional consequence, you're looking for a different assay type, what have you, you can click to the second most prioritized reference. And again, high level at title abstract or granular level at the sentence fragments, see exactly why it was prioritized and make a determination about its relative merit for your variant interpretation and classification. So the next piece of this second example that I want to describe, we've alluded to in the form of that hexagon of various genomic associations. One of the ways that you can modify your search for enhanced specificity would be adding a phenotype. You can also add multiple phenotypes. I've just randomly selected some. You'll note that when you add multiple key terms, you have the choice of electing an AND operator or an OR operator, which would be more restrictive or more broad, requiring both or one of those terms to be in any of the references that are returned. Similarly, you can add across multiple categories. In this case, I'll type in a disease and a phenotype. And you could go even further, and I mentioned the fact that we index according to various therapeutic compounds, all the way from aspirin to dabrafenib, so and everything in between. And then lastly, you can perform the free text search that I had described before. So again, if you've got a very broad result set, which typifies some of your cancer searches, cancer-related genes, and say thousands of articles, and you want to get at the specific article that talks about a particular BRAF variant in the context of non-small cell lung cancer, where dabrafenib is the treatment, and you're looking for Kaplan-Meier survival data. That's a possibility using Mastermind's enhanced specificity capability. So that's the second example. The third example, where in the first example there was fewer than a dozen search results. The second example there was more than a dozen. The third example of a typical result will be when there's no results that Mastermind returns. So that's a no result. The benefit that Mastermind provides in this case is threefold. The first is that it allows you some quantitative measure of confidence that there is no article that ever mentions your variant because of Mastermind's comprehensive indexing of a very broad content set, as well as how comprehensive and accurate our genomic language processing capability is. So that's the first, is confidence. The second is your ability to see related variants very quickly, in this case by filtering your variant results by typing in the residue, and where your specific variant is not found in Mastermind or in the literature at large. There is, at that residue, a number of variants that are cited, including this arginine to glutamine change, which is mentioned in 20 references. And that may very well inform your variant interpretation according to ACMG or AMP. And then the third and final thing that a Mastermind allows you to do in the face of a null result is create an alert for this variant so that an email can be sent to the user account that you're searching under the week or the month that that variant is newly published in the literature. So that allows the data to come to you rather than you needing to go out to find that data. So those are the three basic search types in Mastermind, where I touched on the sensitivity and specificity aspects of Mastermind's results and feature sets. Let's go through another 6 examples. I'll go through them fairly quickly, where I'll be able to expound even further on the sensitivity specificity aspects, many of which Steve alluded to in his discussion. So the first is myelin protein 0, which is the Charcot-Marie-Tooth gene. I've searched on a pretty well-covered variant, the serine 63 deletion variant, which is found in about 50-some articles. I'll showcase the way that the author described the article in many of these references. You'll note, obviously, that as I toggle from paper to paper, most of those references talk about the variant as S63del, but some of them, including this paper from 2003, talk about it as S34del. So that's a reflection of the legacy nomenclature that plagues descriptions of variants in this gene, and that results from the protein having a signal peptide that, when cleaved, can, depending on where the authors begin their nomenclature, can start the variant numbering at different positions along the protein axis. So in this case, this author didn't include the signal peptide in their numbering and described the serine 63del variant as serine 34del. Mastermind found that, was aware of the legacy nomenclature as it is very broadly across the genome, and disambiguated it and put that result in and amongst the rest of the S63del descriptions for maximal sensitivity based on our awareness of the legacy nomenclature issues for this protein. So that's the fourth example. The fifth example will be, we'll touch on actually some of the things that Steve had spoken to. So this is now an OTC variant. You'll notice if you're familiar with this kind of nomenclature that it's in the 5' UTR region with that -365 G to A change description. And here I have two drop downs in my Mastermind search box. I'm going to go through both of them and showcase the value of those. I'll start with the 5' UTR, which, as Steve described, will now bucket all of the variants in Mastermind's data that appeared within that OTC 5' UTR. So when I execute that search, what you can see here now, when I go to one of the prioritized references out of 9 and showcase the variants that are matched, is any of the variants that the author described that fit into that bigger bucket of the 5' UTR. Those are all depicted in this matched column in the variant sentence fragments. And that's true of any of the references as you toggle through them, whether or not it was the self-same cDNA change that you searched on. You'll notice as I toggle through, some of the papers do mention that variant, others of them don't. And what Steve had alluded to earlier was if you make a declaration of a specific interest in that precise nucleotide change by engaging this variant dropdown in Mastermind, Mastermind will show you which of those articles do explicitly mention that nucleotide change and will demarcate them by this target icon, which now for those two papers that do mention the -365 G to A change, those are maximally prioritized because you as a user declared your interest in that nucleotide. And then you can see right away in the variant sentence matches that yes, indeed, that very variant was mentioned in those papers. So Steve, I don't know if you have anything to add there before I move on to the sixth example.
Sure. One thing you'll notice between the two searches that Mark just performed are that it's the same 9 articles in the results. So one question you might have is, why would I select the second suggestion that just says 5' UTR if it gives me the same 9 articles, just not as well prioritized for the particular variant I'm looking at? And the answer is because this is one particular case where the cDNA nomenclature only has one protein description, at least in part because it's in the 5' UTR. There are not multiple transcripts that would cause differing nomenclatures for a given variant. So for other examples where you might have overlapping transcripts that actually describe different locations, selecting that the protein description might actually be more specific because you're saying, don't give me articles that use this other protein description, which tells me it's in a transcript that I'm not currently interested in. And so that's the reason you might select the protein description, because in some cases, again, depending on how the transcripts line up, how the nomenclatures result from the transcripts, you might end up in a scenario where selecting the protein suggestion actually is more specific rather than less specific.
Great. Thanks, Steve. So the sixth search example, again, builds on some of the concepts that Steve talked about, where you can see in this search example, in addition to the cDNA specific query, for this synonymous variant, I also have the option of selecting on that protein level query, which again is bucketing those results and doesn't prioritize because you didn't declare a specific interest in the C dot change. The third option that you'll see, I'll call your mind back to that slide that Steve talked about, the splice region donor bucket. So this is a perfect example, an illustration of what Steve was describing, where this is a synonymous change, but you may very well be interested in knowing whether any close by changes in that splice region have been shown to perturb splicing in the ATM gene at that region. And so if you are interested in seeing more broadly or more sensitively any of those variants in that region and how they may impact splicing, that last variant dropdown SRD is what you would choose, as opposed to selecting one of these two where you make a declaration of an interest in that specific nucleotide change or more generically that protein level change. The seventh example here, again, is related to that search, where instead of a coding change, now we have a non-coding change. So this is a -2A to C change in one of the intronic regions toward the splice acceptor in ATM. Again, if you elect to search on the cDNA change, you're going to have all of the results in that splice acceptor region in your result set, but you will have those targets that prioritize references that specifically mention the -2A to C change, versus if you select on the SA, you'll have them brought together with a more generic relevance calculation where you're, say, less interested in the precise nature of that nucleotide change, but just want to see any of the splice effector changes in any of the variants that Mastermind has indexed. So the last two examples that I have will be searches at the RSID level. And this is an interesting example because many of you may not be aware that RSIDs are not mapping one-to-one to specific nucleotide variants. Some RSIDs have multiple nucleotide changes, as you can see in this search result. So Mastermind, for this BRAF V600 change, this RSID can be A, E, or G. If you're agnostic, you're indifferent to which of those changes you'd like to search for, you can select on the RSID and execute your search. And then, similar to what Steve described, you can see up here the various ways that that protein level change has been described and the number of times that it's described in any one of those references. And then if you select on one of those, you can add that to your multi-parameter search and basically force the papers in a maximally specific way to mention the BRAF V600G change, as I've done here. And you'll note that here with that target, just as Steve alluded to before. So the last...
Mark, you have about 1 minute.
Yep, I just have one example. I can do that very quickly. So the last example will be a reflection of the way that Mastermind allows you to perform searches at the genomic coordinate level, which is a use case that many of our users have coming right out of their sequencing workflow queues. This is just a simple example to say that Mastermind is aware of genomic coordinates and how they map onto the different genes, different transcripts of different genes, as well as if there's any overlap in genetic elements. Mastermind is aware of all of those in the context of the human genome. So Candace, that was what I wanted to show our users, and I'm happy to pass it over to you and stay a little bit longer for anybody who has questions.
Thanks, Mark. I think that we're not going to be able to properly answer any questions in the time we have left. So what I'd like to do is gather all the questions from our question box. Thank you so much, everyone, for your questions. And we'll have Mark and Steve take a look at those and work on those, and we'll post them. I'm trying to put my screen back up, but we'll post them on our website along with the recording of the presentation. Thank you so much to Mark and Steve for the awesome presentation. And I just have a few closing remarks. If you don't have a Mastermind account, you can sign up at bit.ly/mastermind-masterclass, and we'll get you set up. And follow us on Twitter at Genomenon, and look for an email with details on our next event there and in our email. If you'd like to talk to a member of our team about upgrading to Professional Edition, or you have questions about purchasing multiple seats for your lab, please email us at hello@genomenon.com. And thank you again for joining us. We hope you'll join us for our next Mastermind Masterclass, and enjoy the rest of your day.